Okay, I'm going to consider another group. I'm going to consider n by n matrices with real entries and non-zero determinant. Determinant. You'll recall that a matrix is invertible if it has a non-zero determinant, and that'll crop up later. Closure, neutral, inverse, associativity. So we need to show these. Well, closures are obvious because the product of two n by n matrices is an n by n matrix. You'll remember you get your matrix like this. You'll bring the top row up to that one, this one, you do the rows with the columns, and you get another matrix. Brilliant. Actually, we haven't shown it's closed. All we've shown here is that the product of two matrices, two square n by n matrices, is another n by n matrix. We haven't shown it's got a non-zero determinant. But we do know that because we know that the determinant of AB, where A and B are matrices, equals the determinant of A times the determinant of B. Just a minute. B. So if the determinant of A is greater than 0 and the determinant of B is greater than 0, that tells us that the determinant, sorry, not equal to 0, not greater, not equal to 0. AB is also not equal to 0. So that checks out because my definition of my ground set here is n by n matrices with non-zero determinant. Neutral. Yeah, you'll know that the matrix with ones on the major diagonal, 0 elsewhere, is the identity matrix, and so that checks out there. Neutral or identity, I guess. Inverse. Well, if the determinant of a matrix A is not equal to 0, then A to the minus 1 exists. So that's right. And then, of course, matrix multiplication is associative. By design. That's why you define matrix multiplication like that, to have this nice associative property. So matrix multiplication of n by n real matrices with non-zero determinant is a group, and I'll return to this example quite frequently in the course. Okay, stop there.